Welcome to Grandeur Decoded, where we dissect the strategic genius behind the world's most spectacular creations. The most expensive thing ever built by humankind was the International Space Station, a monumental $150 billion endeavor requiring the collaboration of 15 different nations. Yet right now, a private company is building something even bigger, taller, and exponentially more ambitious: the Starship. It is the first machine in history designed not just to visit orbit, but to reshape human civilization entirely. It's a gamble, a logistical nightmare, and a masterpiece of strategic engineering that is utterly rewriting the rules of spaceflight. But to truly appreciate this monster of steel, you need to look past the height and focus on the cold, hard logic that makes its impossible goal, a Mars colony, even remotely feasible. That is exactly what we are going to decode today, starting with the singular strategic choice that makes all the difference. 10 decoded facts about Starship. The strategy behind the impossible rocket. Fact 1. You need to know is that the Starship program isn't designed to be a competitor to traditional rockets. It's designed to be a competitor to Boeing 747s. The entire strategic foundation of the program is built on a radical, financially driven metric called mass to orbit per dollar. NASA's Ares iRocket, for example, aimed for around $25,000 per kilogram to orbit. Starship's long-term operational goal isn't just to beat that, it's to reduce the cost to under $10 per kilogram. This number is the silent strategic core of the whole mission. Achieving that ultra-low cost threshold completely flips the economic model of space travel, moving it from a scarcity problem, where every gram matters, to a volume problem, suddenly making mass colonization and orbital construction financially viable. It's a ruthless exercise in supply chain domination, not aerospace refinement. And that strategy leads directly to fact 2, which is the most unconventional engineering choice of the entire design: stainless steel. Every major aerospace program for the last 50 years has relied on advanced, brittle, high-cost materials like aluminum-lithium alloys or carbon fiber. When Starship was revealed, aerospace engineers across the globe scoffed. Steel is heavy, cumbersome, and ancient. But here is the decoded detail. At the extreme heat of atmospheric re-entry and the cryogenic temperatures of liquid methane fuel, steel actually performs better than those exotic composites. Its strength remains high, and it expands and contracts less violently. Crucially, stainless steel costs about $3,000 per ton, while aerospace-grade carbon fiber costs about $130,000 per ton. When you are building a rocket that is 50 meters tall and designed to be thrown away after 3 orbital flights, the decision to use cheap, easily welded steel is arguably the greatest strategic and financial innovation of the 21st century space race. The third strategic detail that underpins this whole structure is the Raptor engine. Starship requires 33 of these engines on its super heavy booster alone, and they are not just powerful, they are a manufacturing revolution. They are the first operational full-flow staged combustion engines ever built, a complex design that maximizes performance and efficiency. But the true strategic masterstroke is the manufacturing process. Unlike the massive, specialized assembly lines required for other rocket engines, the Raptor is built for volume production, using a high degree of automation and rapid testing in Texas. The goal is to produce one Raptor every 48 hours, treating them as interchangeable, high-volume components rather than bespoke works of art. This allows the rapid iteration strategy, which is one of the 10 pillars of the program's success, to proceed at an unprecedented pace. Now, to get a payload of over 100 tons to Mars, Starship needs fuel, and a lot of it. Which brings us to fact 4, the decisive dance of orbital refueling. The Starship is too big to carry all the fuel it needs for an Earth-to-Mars trip from the ground up. So the strategy relies entirely on sending multiple Starship tanker vehicles into low Earth orbit, LEO, where they rendezvous with the waiting Mars-bound Starship and pump fuel in zero gravity. This delicate orbital procedure, which has never been performed at this scale, is a massive technical hurdle. The program needs to successfully complete up to 6 tanker launches just to fill one ship destined for Mars. This reliance on an in-orbit gas station is the entire strategic backbone of their deep space ambition. And honestly, it's kind of mind-blowing to consider the logistics involved. Fact 5 is the engineering detail that saves the company billions: the grid fins. These massive 4-meter-wide metal latticework structures at the top of the Super Heavy booster look deceptively simple, but they are crucial for two reasons. They manage the booster's descent, allowing it to autonomously steer itself back toward the launch pad with incredible precision, saving millions in fuel and eliminating the need for complex, heavy landing legs. The second function is more strategic. These fins are part of the system that allows the ship to be caught by a giant set of mechanical arms, a process known internally as the chopsticks maneuver. This aggressive, high-risk strategy is designed to immediately place the booster back on the launch mount, allowing for a 60 to 90-minute turnaround time between flights. That's wild when you think about it, making the turnaround time faster than that of commercial aircraft. Every part of the design, from the material choice to the landing fins, is optimized for one purpose: speed and reusability. Fact 6 of the Starship program is the genius of using common bulkheads to reduce weight and maximize propellant volume. Within the Super Heavy booster, the tank holding the liquid methane and the tank holding the liquid oxygen are separated by a single shared wall rather than two separate reinforced domes. This common bulkhead is a structural tightrope walk, as the two propellants must be kept at drastically different temperatures and pressures, but it saves several tons of mass that would have been required for a redundant structure. This tiny engineering choice, repeated across the entire vehicle, is a massive strategic advantage in the ultra-competitive math of orbital mechanics. This focus on maximizing every cubic centimeter of propellant is the hidden cost saver that makes the Starship's payload claims credible. Next, Fact 7 reveals the ultimate goal of the methane-oxygen propellant choice, and it has nothing to do with Earth. The real strategic payoff of using methane, CH4s, and oxygen, LOX, is that these can both be synthesized on the surface of Mars using a simple process known as the Sabatier reaction. By transporting a small industrial plant, Starship can use the CO2 in the Martian atmosphere and any water ice to create new fuel. This is the linchpin of the Mars colony plan. The first few missions bring the people and the factories, and subsequent missions refuel in situ on Mars. This decision made years ago fundamentally defines Starship as an interplanetary vehicle, a strategic move that no other current government or private program can replicate. The strategic depth continues with Fact 8, which centers on the point-to-point Earth transport capability. While we focus on Mars, Starship is also designed to be a global traveler. The concept is that the Starship could launch from a floating ocean platform, enter a brief suborbital path, and land on another floating platform anywhere else on Earth in under 1 hour. The vehicle is designed to carry up to 100 passengers in this configuration. This is not just a high-speed travel fantasy. It's a strategic economic lever. Generating high-value revenue from commercial terrestrial transport could single-handedly fund the entire long-term Mars development program, turning the Mars vehicle into a sustainable financial engine here on Earth. Fact 9 is the ultimate structural test of the rapid design strategy: the ceramic heat shield tile system. Unlike the thick, one-time ablative shields of the Apollo era, Starship uses thousands of hexagonal ceramic tiles that are designed to be reusable. This presents an engineering headache. Tiles must be fixed perfectly to a steel hull that expands and contracts wildly during flight and re-entry. However, the use of this reusable shield is the only way to achieve the aggressive turnaround times necessary for the $10 per kilogram cost goal. It is an engineering compromise born of a ruthless strategic commitment to reusability at all costs. The program accepts the risk of losing a few tiles in exchange for the long-term strategic win of making the entire system reusable, a risk that has defined its public testing phase. Finally, Fact 10 is the true scale of the plan: the massive propellant capacity. To understand the raw power of the Super Heavy booster, you need to understand the fuel inside. It holds approximately 3,400 metric tons of propellant. That's over 7.5 million pounds of liquid methane and liquid oxygen. To put that in perspective, the Saturn V rocket that launched the Apollo missions carried about 2.8 million kilograms of propellant. The Super Heavy carries significantly more. This overwhelming capacity isn't just for lift. It's the raw strategic power required to launch the heavy tankers, establish the fuel depots, and execute the complex orbital refueling ballet. It is the raw, brute force answer to the problem of deep space travel designed to overwhelm physics with sheer scale and efficiency. The Starship program is not defined by its accidents or its delays, but by this intricate, almost maniacal commitment to a singular, revolutionary financial model, fully and rapidly reusable spacecraft. Every detail, from the choice of steel to the audacious chopsticks landing, is a calculated strategic move toward achieving a goal that shifts humanity from a single-planet species to an interplanetary one. The grandeur here isn't just in the steel, it's in the decoded strategy of making the impossible inevitable.